Okay, hello everyone. So, okay, hello everyone. So we have finished the three well generalized neural random field for the hand. So now I will introduce some of more theoretical work, which is about the signal propagation in transformer, theoretical perspective in the Rhodes brain collapse. Is it published in the Neuroscience 2022? So as it's called, the transformer is composed of stack of transformer block. The core operation is the attention mechanism. So as you can see, the output of attention layers is a linear combination of the importance weights and the value. Then the architecture includes a fully connected layer, residual connection, and the layer normalization. So this work for inspiration from the work before, who showed that if the residual connection are not used, the representation of the input layer, they will converge to a rank 1 matrix, therefore exponentially fast with the depth, where in the end, all the token representation are identical. So there are two main questions left for us to resolve. The first one is, how does the rank collapse affect the training? And the second is, are the residues connections is truly enough? So actually, when people introduce the transformer, they name their paper as a attention is all you need. But then, yeah, there are some newer paper, they call that like the attention is not all you need. Actually, the attention will lose the rank exponentially with the death. So this paper, they show that the skip connection are essential to avoid the collapse state. And at the same time, the skipless transformer, they will quickly converge to rank 1 matrix. So in addition, it's a well known that training transformer require a combination of tricks. The most important is the adaptive methods, the layer normalization, and the learning rate warm-up. But even when all of these techniques are used, the effective training is not guaranteed. So yeah, it's the intuition that most deep transformer models, they use the free layer normalization configuration. So motivated by those questions, the author first saw that high alignment of token representation as initialization caused vanishing gradient. And they show that the depth dependent scaling over several branches preserve rank and stabilize the norm. And thirdly, there exists factors that affect differently the gradient of the network parameter. So let's start by the first questions. The rank collapse cause the vanishing gradient. So in the lemma 1 is a paper block with respect to its parameter, the value, the theory. Here we can see that the W, they indicate the one of the key theory or value. So given the questions 1 and 2, they are able to show that by introduce a loss function, then under the rank class, we can have the vanishing gradient phenomena. which will hurt our training process. And by the theorem 3.2, they can conclude that the rank collapse issue corresponding to an initialization in a region of vanishing gradient. And this answers the question. So let's move to how to collapse. So we now turn our attention to the study of the skip connection in the transformer. So I would remind you that some previous work they show that simply adding the skip connection will prevent the rank collapse. So they study the correlation between different tokens. And in the figure, you can see that by using the appropriate residual scaling, we can control the correlation between tokens. Here, the correlation equal 1, meaning that the two tokens are identical. And we are, as in this figure, we can see that if we do not use the scaling, the correlation rapidly go to 1 as the depth increase. So then they prove that without the depth dependent residual scaling, like with and alpha 2 is 1, so the correlation between token, they will quickly increase and reach the perfect alignment. This is formalized by theorem paper 3, where they show that if we choose alpha 1, alpha 2 depend on L as 1 over square root to L, we have the behavior that's described in equation 15. On the other hand, in the case where alpha 1 and alpha 2 are just some constant independent on L, the correlation between token goes to 1 when the depth increases. So this observation is consistent with previous finding concerning about the downscaling residual weights in resonance or transformer. And now we move to try to understand better what are the different factors that affect the gradient of with respect to the parameter of the carries and values. So for this part, we are going to assume that there is some constant correlation, expectation between any two tokens of the same layer. So now we have the expected norm of gradient, and it's revealed that different factors affect differently the gradient with respect to the value and the carry. Also the key, because the key and the carries are similar. So more specifically, there is a cubic relationship with respect to the norm square for the carries compared to just a linear one for the values. Also the sequence length and effect of parameter. So they speculate that by adaptive methods have been known to outperform train. So based on the expression of the gradient we already did, these propose very simple architectural modification. Now they have this inverse temperature scaling inside the solution. They can set the temperature in such a way so that the expectation of the gradient of different parameter match. And now about doing this very simple trick, we cannot train comparative transformer using just plugins. Their experience among the German to English translation tasks, they reveal that this simple trick significantly boosts the expected result when training transformer with just HED, and the same result can be observed in the vision task. So to summarize, they have uncovered that the rank collapse causes a vanishing gradient for the key and queries parameter. They also discovered that the existence of residual connection is not enough. They need to be appropriately scaled. And since the increasing correlation can significantly expand some difference in the gradient of different parameters in the network, even when we actually controlling the correlation, there is some other factor that affect the gradient of different parameters in a similar way. Some research ideas we can get from this paper is that we can improve the optimization of transformer models, or we can try remove the skip connection and normalization layer, and we can investigate the relationship between the entropy collapse and the training stability. So currently, the only strategy to deal with the rank collapse is a skip connection. Maybe we can try to remove the skip connection by modify the attention mechanism, and then we can apply some framework like the deep kernel sharpening or Taylor activation transformation, like to achieve where we have signal propagation. And yeah, sure, we can apply those ideas to the vision transformer. Yeah, that's it from me today. Thanks for listening. Feel free to have any questions if you have.